Hi everyone, and welcome to this week's Udacity Deep Reinforcement Learning Nano-Degree Weekly webinar. I'm going to this week focus on actor-critic methods, which I probably could have gone on before PPO algorithm, but I'll talk about it now just to give you a bit better idea. So basically what I'll cover, I'm going to go through the preliminaries and just go back through some basics, introduce policy gradient, summary of common baselines, actor-critic methods. I'll go back to the baselines a bit more and then go back into A2C and A3C and the differences. And then I will basically put together implementing A2C in PyTorch and then have a bit of a Q&A. So previously we derived policy gradients and implemented the reinforced algorithm known as the Monte Carlo gradient. There are, however, glaring issues with the vanilla policy gradient, noisy gradients and high variance. Why does this happen? Recall the policy gradient. As you can see, that's the policy gradient. Okay, so the expectation given the states and the sun, and basically that policy is getting the return there based on the rewards. So, as in the reinforced algorithm, we update the policy parameters through Monte Carlo updates, taking random samples. This introduces the inherent high variability in log probability, log of policy distribution, and cumulative reward values, because each trajectory during training can deviate from each other at great degree. Consequently, the high variability in log probabilities and cumulative reward values will make noisy gradients and cause unstable learning or the policy distribution skewing to a non-optimal direction. Side high variance of gradients. Another problem with policy gradient occurs. Trajectories have cumulative reward of 0. The essence of policy gradient is to increase the probability for good actions and decrease those bad actions. Actions in the policy distribution, both good and bad action, will not be learned if the cumulative reward is 0. Overall, these issues contribute to the instability and slow convergence of vanilla policy gradient methods. Improving policy gradient, reducing variance with baselines. One way is to reduce the variance and increase stability in subtracting the cumulative reward by a baseline. In theory, making a cumulative reward smaller by subtracting it with a baseline will get a smaller gradient and thus smaller and more stable update. And basically, they're subtracting from the cumulative reward. Here is a very illustrative explanation taken from Jeremy Lowe. For the sake of hypothetical example, let's say that the log of the policy is 0.5, 0.2, and 0.3 respectively for 3 trajectories, and the reward is 1,000, 1,001, 1,002. Then the variance of the product of the two terms for these 3 samples is the values 0.5 times 1,000, 0.2 times 1,001, 0.3 times 1,000, which according to Wolfram Alsa is around 23286.8. Now, what if we reduce all of the reward by a constant, say 1,001, and then the variance of the product becomes the value of 0.1 times 1, or 0.2 times 0, or 0.3 times 1, which is 0.1633, a much smaller value. Baseline can take various values. The set of equations below illustrates the class variant of the actor-critic method with respect to reinforce. In post, we will take a look at the Q actor-critic and advantage actor. As you can see, this is just the base reinforce, and the actor-critic has the Q value. And then you've got the advantage actor-critic, which instead replaces that. And then you've got the TD, which replaces it again. Before we return to baselines, let's take a look at the vanilla policy gradient again to see how actor-critic architecture comes in and what it really is. Recall that, as you can see here, that's just the vanilla one to get the actor-critic. So if we decompose the expectation into, so here's the states of actions, And there's the expected reward, which is GT, given the action and the state of that policy. The second expression should be familiar, is the Q value. If we did not know this already, I would suggest that you read up on value iteration and Q learning. And so it's going through using, so this is basically a Q. Plugging that in, we can rewrite the update equation now with the Q, which gives us an actor-critic method. As we know, the Q value can be learned by parameterizing the Q function with neural networks denoted by a subscript weight above. This leads to an actor-critic methods where the critic estimates the value function. This could be the action value, the Q value, or state value, the V value. The actor updates the policy distribution in the direction suggesting that the critic, such as the policy gradient, and both the critic and the actor function as parameterized with neural networks. In the version above, the critic neural network parameterizes the Q value, so it is called the actor-critic. Below is the pseudocode for the actor-critic. As illustrated, we update both the critic network and the value network at each step. So we initialize the parameters, then we sample through the rewards on each things based on probability, then we sample the next action, update the policy gradients, compute the correction TD or action value, and we use update to parameterize the Q function. Then we move on. Okay, back to baselines. To make an argument from authority, as I was always able to find a reason why the state value function makes an optimal baseline function is stated in Carnegie Mellon Berkeley lecture slides, but with no reason provided. So using the V function as the baseline, or the value function, as the baseline function, we should track the Q value term with V with value. Intuitively, this means how much better it is to take a specific action compared to the average general action at a given state. We call this the advantage value. Does that mean that we have to subtract two neural networks for both the Q values and V value in addition to the policy? No, that would be very inefficient. Instead, we use a relationship between the Q and the V from the Bellman optimality equation. So we can rewrite the advantage as the following. Then we only have one neural network for the V function parameterized by V above. We can rewrite the update equation. This is the advantage actor-critic. So the advantage actor-critic has two main variants, asynchronous advantage actor-critic, A3C, and the advantage actor-critic, A2C. A3C was introduced by DeepMind's paper, Asynchronous Methods for Deep Reinforcement Learning. In essence, A3C implements a parallel training where multiple workers in parallel environments independently update a global value function, hence asynchronous. One key benefits of having asynchronous actors in effective and efficient exploration of the state space. A2C is like A3C but without the asynchronous part. This means a single worker variant of A3C. It was empirically found that A2C produces comparable performance to A3C while being more efficient. According to OpenAI blog, most researchers aren't completely sure or how the asynchronous benefits learning. After reading the paper, our researchers wondered why the asynchronous led to improved performance. Perhaps the added noise would provide some regulation exploration, or if it was just an implementation detail that allowed faster training with CPU-based implementations. Our asynchronous A23 implementation performs better than our asynchronous implementation. We have not seen any evidence that noise introduced via asynchronous provides any performance benefits. This A2C implementation is more cost-effective than A3C when using single GPU machines, and is faster than CPU-only A3C implementations using larger policies. However, we have implemented the A2C in the post, and more simple in implementations, better for the computer multi-process for A3C is daunting. So recall, the new update equation replacing the discounted cumulative reward from the vanilla gradient with the advantage function. So there. Now, implementing A2C. On each learning step, we update both the actor parameter with policy gradient and the advantage value, and the critic parameter with minimizing the mean squared error with the Bellman update equation. This is how this looks like in code. Below includes the hyperparameters. So we've imported all, we've got the hyperparameters, we've got the gamma, the number of steps we're going to do, and max episodes. Here's the actor-critic. So we've got the number of actions, and we've put in a critic, and we've also got the actor. So it forwards it through the state through, and we basically unsqueeze it. We do a reload through the critic, and then the other critic, and then the policy distribution is the relay of the actor linear state, and the actor linear, which is the actor. And then we get the policy and the policy distribution. The A2C, so basically like anything, we get the environment, the action space, we add in the policies, we set all the parameters, and then we start a for loop. So we go through the max episodes, which has been set, we get state, and we pass the state through to the actor-critic forward, and we get the returns. We then, the action is random choice, and then blah, blah, blah. So basically, reward value, we append that all. If done, we go through all the rest of it. We compute the Q values, update the actor-critic, and pretty much go through till we plot it all out. Now, once we plot it, running the code, we can see the improvement. So it basically improves over time. So if we go back, that's just basically plotted out, and we're just using the normal optimizations and steps. And so there we pretty much have the A2C. So if you've got any questions, please feel free to ask them now. You don't have any questions, so well, thank you very much for this week, and I will get on to some other stuff for you next week. Thank you.